Have you ever wondered how your smartwatch counts your every step? Or how a drone just hangs there in the air perfectly still? Well, the secret is a tiny, powerful brain called a microcontroller. And today, we're looking at a really special one, the DarkLight. This board was developed 100% by Ghanaian engineers. It's all about inspiring new, innovative solutions for local problems right across Africa. So let's dive in and see how it can bring your big ideas to life. Right, so behind every one of those cool self-balancing robots, every smart drone, every automated gadget in your home, there is a little computer on a single chip. That's our microcontroller. It is literally the brain of the whole operation. So the big question is, how does it actually think? To really get how these chips work, we have to start with their native language. And honestly, it's a super simple language of absolutes. Black and white, yes or no. It's the language of the digital world. At its very core, the DarkLight board talks in a really straightforward way, with digital signals. A signal is either on, which means it's carrying 3.3 volts, or it's off, carrying 0 volts. That's it. This simple two-state system is the foundation for, well, pretty much all of modern computing. Okay, a quick heads up for anyone just starting out. You're going to hear developers use a bunch of different words for on and off. Off might be called low, or false, or logic 0. And on might be called high, true, or logic 1. Don't let it throw you off. They all mean the exact same thing. So how do we actually make this do something in the real world? Well, the classic first project, the hello world of electronics, is making an LED blink. With DarkLight, it's super simple. You connect your LED, use the digital out command in your code, and then you just tell it to write a 1 to turn it on and a 0 to turn it off. This right here, this direct link between code and a physical light, this is where the magic really begins. But let's be real, the world isn't just on or off. It's full of gradients, nuances, and everything in between. To understand that, we need to step into the analog world. Think of it this way. A digital signal is like your standard light switch. It's either all the way on or all the way off. But an analog signal, that's like a dimmer switch. It can be at any level in between. And this is absolutely crucial for sensors that need to measure things that change smoothly, like temperature or light or sound. So how does our digital brain, which only thinks in on and off, understand this nuanced analog world? Well, it uses a built-in translator. It's called an analog to digital converter, or ADC for short. The ADC's entire job is to measure that smooth, continuous voltage from a sensor and convert it into a digital number that the microcontroller can actually work with. So what's with this number, 4096? Well, this tells us just how precise the DarkLight's ADC is. It's a 12-bit converter, which means it can tell the difference between 4096 different voltage levels. It's not just seeing on and off, it's seeing 4094 distinct steps in between. That allows for some seriously fine measurements. Okay, so we can read the analog world with amazing precision. That's cool. But what about the other way around? How do we create an analog-like effect, like smoothly dimming an LED or controlling a motor speed, when all we have are our digital pins that can only be on or off? The answer is this really clever trick called pulse width modulation, or PWM. Since a digital pin can't output a half-wave voltage, we just fake it. We switch the pin on and off thousands of times a second incredibly fast. By changing how long it's on versus how long it's off, we can simulate an average voltage. It's a brilliant little piece of engineering that lets a digital brain have analog-style control. The key idea behind all of this is something called the duty cycle. It's just the percentage of time the signal is on during each of those super fast cycles. So a low duty cycle, say it's only on for 10% of the time, gives you a low average voltage and a dim LED. A high duty cycle, maybe 90% on time, gives you a bright LED. It's this precise control over that on-off ratio that gives us that smooth analog-like feel. All right, so now we can read its sensors and control outputs with all kinds of nuance. But what really makes a device feel smart is its ability to react instantly and efficiently. Let's figure out how to build a truly responsive system. This quote really just nails the problem. Imagine you're building a safety system for a factory. You can't have your main processor wasting all its energy just constantly checking a sensor, asking, is the gas level high yet? How about now? Now. It's a huge waste of brain power. The much smarter way to do it is with something called an interrupt. The microcontroller can just be humming along, doing its main tasks, but when a high-priority event happens, like someone presses a button or a critical sensor goes off, it sends an interrupt signal. The chip immediately pauses what it's doing, runs a special little function to handle the important event, and then jumps right back to its original task like nothing ever happened. It's kind of like tapping someone on the shoulder for something urgent. So interrupts are great for those sudden, important events. But what if you just need to juggle a few ongoing tasks at once? Like how do you blink an LED every single second while also checking a sensor every 100 milliseconds? For that, DarkLight has this awesome feature called a ticker. You can just think of it as a simple scheduler or a little personal assistant for your code. You can tell it, hey, run this function every 500 milliseconds and run this other function every 200 milliseconds. It just handles all the timing in the background so your tasks can run side by side without getting in each other's way. So our device is now responsive and it can multitask. It's getting pretty smart. But to build really powerful, complex systems, it can't be an island. It needs to be able to talk to other components. The thing is, a single microcontroller can't do everything by itself. For more complex projects, you're going to need to connect it to other specialized chips, things like displays, memory cards, or really advanced sensors. And to do that, they all have to agree on a common language. We call these communication protocols. One of the most common high-speed protocols you'll see is called SPI. It uses 4 main wires. You've got a clock to keep everyone in sync, a MOSI line for our DarkLight, the master, to send data out, a MISO line for the other device, the slave, to send data back, and a chip select line so the DarkLight can pick which specific device it wants to talk to. But SPI isn't your only choice. It's always about using the right tool for the job. Another really common one is UART. Now, it's slower and only uses 2 wires, but it's absolutely perfect for devices like a GPS or a Bluetooth module, where raw speed isn't the #1 priority. So let's do a quick recap of the building blocks we just covered. We have digital controls for simple on-off actions. We have analog and PWM for reading the world and controlling things with nuance. We have interrupts and tickers to make our projects responsive and able to multitask. And finally, we have communication protocols to connect to a whole world of other electronics. And these aren't just abstract ideas. This is your toolkit. These are the fundamental principles you're going to use to turn any simple idea into a smart, interactive, and connected device. So you have the blueprint now. You understand the language these tiny digital brains speak. The question is no longer, how does this even work? With these powerful building blocks created to empower innovators right here in Africa, the real question is, what will you build first?